Hello and welcome back to Calculus 3, section 13.3, double integrals in polar coordinates. There was a little review last class on polar coordinates where I gave the, actually going to change these into reds. I gave the little introduction review of polar coordinates and the way, what they represent, the way they work and all that stuff. So what we see over here are the rectangular coordinates, and they're called rectangular coordinates because we move in a rectangular fashion to go from the origin 0, 0 or 0, 0, 0 to a point. And then I told you that there are these polar equivalents where the Cartesian rectangular coordinates will have r comma theta, and then the the rectangular in 3D will have either cylindrical or spherical, which is our next lecture. We'll see all of those coordinates, or the following one, whatever. I derived the conversion formulas, and these conversion formulas are used to change polar into rectangular or rectangular into polar, because we need to be able to switch these functions. And then I just did some basic examples on flipping functions and showing that these particular coordinates, rectangular and polar, are not competing against each other, they complement each other. So what's beautiful in one domain is ugly in the other, and vice versa. So now we are going into this integration business, and what we've seen in 13.1 is the rectangular domain. Then in 13.2 we've seen general region, right? So domain was whatever, intersection of two functions, and then you have a stencil, right? Building up the object in z direction. And now, instead of having the xy standard plane, we are going to have the rectangular, we are going to have the polar graph. So polar graph is actually a circular domain like this. And sure, we still have x and y axis because it needs to provide the origin in the middle. But we no longer care about having the x and y points and x and y coordinates and the way to get to them. What we care is the length of radius r and how much we have to swing that from the away from the x-axis. So actually our polar domain is partitioned through these angles. Now what's important to realize is that for your rectangular domains, which is both 13.1 and 13.2, even though it's general regions in 13.2, you had a representative rectangle delta x. Well, now you are going to have representative pizza slice d theta, because so here let's draw representative pizza slice d theta, and that's the one that spins around. So now if I want to create a 3D object, I can do so by spinning this d theta on the domain. So if I have, let's say I have a ball, right? So sphere, Now d theta in this case would be theta is in between 0 and 2 pi for the entire ball. It has the radius r. So that's for the sphere. But then if I want only half of the sphere, so I go like this, right? If I have half sphere, then our d theta should be 0 to pi, let's say. You can, whatever. So we will have to focus on the domain and figure out things in there. Now we're also going to have dr, which is how far out you are going along d theta. So the infinitely thin slice, pizza slice, d theta, is going to be also stretching in size. So you might have a very long slice, very short slice. But they're all going to be very, very narrow. So now, what is the theorem that we are going to use to compute this? And all of this will make sense once I write it. So we are going to say that we have double integrals over polar rectangular regions. And this word rectangular in this context doesn't mean rectangle, and that's a little bit tricky, but we'll deal with that. So double integrals over polar rectangular regions. So this is one of those times when, wording in mathematics creates a problem. We just spent time figuring out that polar domain and rectangular domain have nothing to do with each other, right? And here's the title, right? Bind together. Well, a rectangular over here is not in a sense of rectangles, but in a sense that all of your limits are integers, are numbers. Because the non-rectangular one, the general one, is going to be functions. You remember the difference between 13.1 and 13.2? Well, this is going to be now difference between the polar rectangular region and the polar general region. Again, rectangular doesn't mean a rectangle. There are no rectangles here. You're talking about d theta. D theta is the pizza slice. It cannot be a rectangle, right? It's closer to a triangle. This over here is arc length. So it's not even a triangle. This is really a pizza slice that is infinitely thin. It's the best way to know, because you know that crust is going to be curved at the end, right? Unless you have a square pizza, and then it's just don't. I've seen it, it's weird. It's like those Japanese watermelon, right? They're square. I understand you want to stack them and, be different, but just don't. Watermelons are ellipsoids, and keep them that way. And have them green, please. That's that. So what do we have? The double integral over, again, here's the rectangle region R, of f of r theta dA is given by f of r theta, and now we have r dr d theta. Let me point out the grade killer. Is everyone looking at the screen? This over here kills your grades. It slays them like nothing, because you forget this. And when you forget this, all of the integration and everything is wrong. So don't forget it. This thing over here is 1 unit. It's separable, right? So r dr d theta. We're going to have a similar string for cylindrical and spherical later on. So you have to have this. So that r there is a great killer. Make sure it's visible at all times. All right, so what do I have? I have the outer integral. That's the first limit. Those are angles, so alpha and beta. And I have the inner integral, which is r, and that's clearly a and b, because those are the values for radius r. So this is the formula. And the word rectangular, so let me circle that and then I'll erase it. So everyone pay attention here. This word pertains to these guys being numbers. That's that. When I swap that with the general, I'm going to put functions in here, just like 13.2 introduced functions for the inner integral. Now that happens in the same section. So we do example of rectangular, and then we switch to the one with functions. Much more interesting. All right, so what do we have over here? Let's say you have a pipe. See, this is a pipe, right? Pipe has hole in the middle, so the stuff can go through it. Now, obviously, if you're a plumber, right, you worry about the size of the pipe because you have different diameters for different purposes, right? The sewage, the water intake, the water outtake, and all of these kind of things, right? So that's a code, and it's important. But then you look also into other engineering applications, not just household plumbing. And then also, if you want to be a doctor, blood vessels. There's just pipes. There's nothing special about it. Right? Yeah, it's some tissue, but yeah, it's a pipe. And it's a cylindrical pipe, has a hole inside, and when that gets clogged, what happens? You die, exactly. There we go, right? So I know it's grim, but it's Calc 3. What are you going to do? So it's important to study these properties. So let's talk about the pipe. So say I have a pipe over here. A pipe is going to have a hole, and that hole is going to go all the way to the bottom. This pipe is going to rest on XY plane. And now we know that we have a circle in the domain. So now, what would domain look like? Oh, actually, I should box this first. That was a terrible box. All right. So what does this domain look like? Two concentric circles. In the XY plane. I'm going to call the top. I'm just going to say that this pipe is 6 feet tall. You all understand what it means for a pipe to be 6 feet tall. It's just a pipe. We want to calculate the volume of this pipe. Now I know when I look at the dimensions, because I can measure it, I'm going to measure 2 inches out So that's 2 and 2.5. So 0.5 thickness on this pipe. So this is your domain. And now I want to set up my double integral. Well, let me draw the representative pizza slice first. What I know in a polar domain, I know that the inner circle has a formula r equals to 2. The outer circle has a formula r equals 2.5. I just noticed that I used 6 feet up there, and then I want to use inches over here. So I'm not happy about that. So I'm just going to get rid of this unit over here of 6 and say that it's going to be in inches. So 6 feet is 72 inches. Right, these are all in inches. You can calculate the radius of the pipe. You can measure the radius of the pipe, actually. And you can measure how tall it is. So now, we need to set up our double integral. So we have a double integral over region R of function is 72 r dr d theta. Well, actually no, first we put dA. And then we go and set up the integral 72 r dr d theta. And then we look at the picture. Now this is very important. What are the limits for theta? 0 to 2 pi. Why? Representative pizza slice starts at x-axis, and then you see those old radars in the movies, they go around, right, like that. That's what the representative pizza slice does, d theta. So, and that's the reason why we have the entire pipe 0 to 2 pi, because this is 0, pi over 2, pi, 3 pi over 2, 2 pi as it spins around. Can I find a half a pipe? Sure. Cut down the pipe. If you cut off this portion, my d theta is 0 to pi. If I cut pipe this way, my d theta is pi over 2 to 3 pi over 2. I can cut pipe anyway. I can cut pipe here and then have from maybe negative pi over 2 to positive pi over 2. That's okay as well. All of those answers have to give you back the same answer because we have a flat top. If the top is cut at an angle, each single one will give you a different answer, right? Because you have a different amount of material, right? Because you have a crooked cut. But since we have a flat top, right, it's symmetric everywhere, that means that you can cut either way. So the limits for d theta, which is representative pizza slice, are pi over 2, 0 to 2 pi. So 0 to 2 pi because we want the entire pipe. And then we go to our r, dr. Well, dr is only where the material is, only where the meat, right? So this part over here is plastic, concrete, whatever they use to make the pipe. It's PVC pipe. So this is a hole. So what is our radius limits? Radius limits better be from 2 to 2.5 because that's where the stuff is, right? If you're calculating the volume of the pipe, how much material? Why do you need that? Well, you want to know how much material it goes to each pipe. Maybe you own the business that makes these pipes. It's a part of the cost calculation. So you can optimize things. Yeah, exactly. Had to use that word. So we want to know the exact volume of the pipe because this one pipe times 10,000 pipes that you have to produce in this week, it's cost, right? So you need to have all of this information as engineer, precise, and then you can make good decisions. So 0 to 2 pi and 2 to 2.5 on this one. Now, if any one of you are freaking out about the extra r and maybe having way too many dimensions, please remember that theta is not a dimension. Theta is the ratio of two lengths in radians. So theta does not bring a dimension to the table. This is equal to the volume because you have three dimensions. Dimension number 1, dimension number 2, dimension number 3. They are all multiplied together. So it is a 3D. D theta does not bring a dimension to the table. So dimensionally this formula is sound, even though it doesn't look like it's sound, because it has four things over there. As soon as you figure out that d theta, right, or not figure out, but remember that d theta is a ratio of circumference, arc length and radius. There you go. Solving this, come on, you just look at it and you know, right? 72 r squared over 2, computed from 2 to 2.5, and I still have the integral 0 to 2 pi in front, and I still have d theta at the end. So integral 0 to 2 pi, 7, that's a 36, and then 2.5 squared minus 2 squared, everything d theta. So that's, you can kick 36 out. I compute the whole thing. 0 to 2 pi, 36 times, now 2 times, well, that's 625 minus 4 d theta. And then we have 36 times 2.25. And then we have the integral. Well, I'm going to put the integral here. It's all constant, kick it out. 0 to 2 pi d theta. Now, the integral d theta is just theta. So this is 36 times 2.25 times theta computed from 0 to 2 pi. Now, obviously, when you plug in 0, theta goes away. So we need to keep 2 pi. So that's going to be 72 pi times 2.25. Now, 2.25, that's going to be 9 quarters, right? So we have 72 times 9 over 4 times pi, and then these guys cancel. So it goes what? It goes in once, and that's 32, so 8 times 9 pi, so 90, and so 108. 108 pi inches cubed. So about 350, right? About 350. What happened? Oh yeah, I multiplied by 2 instead. I multiplied 12 instead of 18. I did 12. It's supposed to be 18. So what is it? 160? 162. Good. Thank you. So 162 times, yeah, I don't know why I did 9 times 2 instead of 9 times 8 in my head. To multiply this quickly in your head, oh, I should have done 18 times 10 minus 18. That's much faster. I did 10 times 9, and then for whatever reason I did 2 times 9 instead of 8 times 9. Anyway. So that's the polar. Let's see if we can find another That's a beautiful example. Now some of you will already be, that's my egg question. Yeah. Z equals 8 minus x squared minus y squared. And the bottom one is z equals x squared plus y squared. And that's that. This is what's given. What's the volume? Right? Since we have a circle over there, should be polar coordinates. It's a round object. So now what do we do with this? Well, I need to know what the domain looks like, and you get the domain when you shine the light on top of the object. It casts the shadow on the xy plane. So this object is almost like a pipe. It's not hollow, right? It's rounded at the edges, and you see that it's fat in the middle, and it's skinny and going into this parabolically, it goes to those shapes. So the object is the fattest in the middle, and if you are to shine the light, it will cast the shadow on the domain, on the xy plane. Now xy plane in this problem is all the way at the bottom. So now what I want to do is I want to look at the domain first. As I'm looking at the domain, all I see is the circle. But I don't know the equation of the circle yet. Now, let's find the equation of the circle. We get the domain when we set two equations equal to each other. So 8 minus x squared minus y squared is equal to x squared plus y squared. This together will give you the circle. Move x squared y squared, we get 8 equals 2x squared plus 2y squared. Factor out 2, cancel by 8, we get a 4, and yay, x squared plus y squared equals 4. So that's what the circle is. 4, 4, negative 4, negative 4. So these are the, right? Domain. I think I have everything I need, except it's a round object. I know I need to do polar coordinates, but these things over here are given in Cartesian. So I have to convert these. So I have to transfer these to polar, because you know what your polar integral looks like. We wrote that theorem earlier. It's a double integral of f r theta. Well, neither of the two functions that are z equals have r and theta in them. So it's your job to convert this. So what is the top function? the top function transferred into is 8 minus r squared. You can factor out the minus sign in front of x squared and y squared. When you factor out the minus sign, it becomes x squared plus y squared, and we know that's r squared. We know that from conversion. If you don't know that from conversion, learn it quickly, okay? Because this formula over here, which is that formula, is a conversion formula between two realms. If you have x squared and plus y squared, that's immediately r squared. So we have that part, and obviously the one on the bottom is much easier to deal with now because that's just equal to r squared. So I have the top shape to be 8 minus r squared, and the bottom shape to be just r squared. Now we know how we deal when we have to find area between two curves and write stuff that is trapped. It's going to be top minus bottom or right minus left. Well, this is top minus bottom situation. So to set up the integral, I have my domain that will help me. Guys, you need the domain for limits of integration. You need these functions here for the inside of the integral, right? None of this stuff is there for decoration, right? We use all of this. So we start by saying that the double integral over rectangular region, right? We're going to end up with numbers everywhere. Of, look what I'm writing here. F r theta top minus f r theta bottom r dr d theta. Don't forget this r. Don't forget the r. So what is this equal to? Top function 8 minus r squared minus the bottom function r squared, all of that times r dr d theta. We are going to take the entire object. We are not going to cut this object vertically or any other way. So that's going to be 0 to 2 pi. It's entire object revolution. It's not cut. Right? And the radius, well, if you look at the picture over here, right, the main radius goes 0 to 4. So this is double integral, 0, 0, 2 pi and 4. And then I have 8 minus 2r squared. No, I'm going to distribute r as well. So it's 8r minus 2r cubed. dr d theta. So what I did is I simplified everything and multiplied by r, so no more r. And now you just integrate. Now it's Calc 1, right? Hence again, no formulas Calc 3 because as soon as you use the formula, you're already in Calc 1. So integral in terms of r, it's going to be r squared over 2, but 2 cancels 8, so it's 4r squared. Minus 2 times r cubed, that's r to the 4 over 4, and it cancels, so r to the 4 over 2. And all of that computed from 0 to 4. And we still have our d theta. So now you will plug in 4. We don't have to worry about 0. It's polynomial. So 0 to 2 pi. And when we plug in 4, you get 16 times 4, 64. Minus 16 times 16 is 256 divided by 2. 256 divided by 2. 1, 2, 8. Right? 1 to 8. Anyone? Who cares, right? Easy. 4 to the 4. That's 256. And then you cut that in half. You get, yeah, 128, good. And then minus 0, everything dies. D theta. 0 to 2 pi. Ooh, I don't like this. Negative 64. So there's a mistake somewhere. Where is the mistake? Yes, it is. Radius in the domain is 2, not 4. I was just testing everyone, so very good. Very good. Radius in the domain is 2. Radius in the domain is 2, which means that's a 2 on a limit, 2 on another limit, 2 on this limit, and now these numbers are different. So 2, 4, 16 minus 8. So we have 8 d theta 16 pi. Nice. When you integrate 8, you get 8 theta, and then you plug in 2 pi for theta, you get 16 pi. So this is the part of figuring out volume of objects using this. And now we are going to switch a gear, and we are going to talk about general region, which is going to have functions in your limits. So for general region, so double integral over more general polar region. We have to use this book. So double integrals over general polar regions. And that is going to be double integral R, region R, of f of r theta dA is going to be the double integral of f of r theta r dr d theta. This is alpha and beta, the outer limits. And now we have to have the inner limits, but as functions, so g of theta and h of theta. So these are the inside functions. So what's different? This thing over here and this thing over here are no longer numbers. They are now functions. Which means that our domain doesn't have to be a circle anymore. You could have a flower stencil. It's okay. You are going to go from 0 to 4 sine 4 theta. Right? 4 sine 4 theta is going to give you 8 petal flower. Now that 8 petal, every time I give you the domain, your next thing to think about is stencil. For what's the name the kids play with it? The Play-Doh, right? Oh wait, actually, wait. What's this called? It's not Play-Doh. This is
clay. It's clay.
Clay. Good. So clay, right? Except you don't use stencil. You don't use stencil, but right, you press. Maybe you can bring a little bit so we can stencil something out next time. Actually, I can fashion it now. You just take this and then take this.
Send you a bill.
Actually, yeah, that's very expensive, by the way. So that's what we have, and we can have whatever type of a stencil. And if you want to have a flower stencil, right, press into clay, press into Play-Doh, press into cookie dough. All right, what you're going to get out of that stencil is, so that stencil is just the outline of your domain, raising walls up. When you push the stencil and take the cookie out or whatever, the top is going to be all wavy and whatever, and that's this. That's the top. The shape of the stencil is over here, and over here, 0 to 2 pi, or you're maybe taking a half of a cookie, a quarter of a cookie, or whatever, right? Or if you're a kid, a Play-Doh, because they eat that, apparently. So, no one? Oh. Good. So let's take a look at homework example and figure it out. I think they did 2 or 3 examples in a textbook, so you can read those. If you're having issues graphing polar regions, you have Mathematica, you have Desmos, and you also have your TI-83 calculators, or 84, whatever. They all do this. So, if you are on Droid, right, you can do this for free, and then you can use it to graph your polar regions. If you are not on a Droid phone, throw it in the garbage and get a real phone, and then you can do this on your phone, right? You just have one step extra than others, right, who already have good stuff. So let's go and take a look at one of these problems. Maybe I should just briefly show, because I don't know if you venture into the book. You see that? Right? Yeah, some cool stuff there. So a lot of these things to compute. So let's do an example of general region. So 33 through 38, we can pick whatever. Region inside the leaf, let's do 34. Region inside the leaf of the rows R equals 2 sine 2 theta. So this is going to be a 4-petal flower in the first quadrant. So in quadrant 1. A quick graph. And we are focusing here. The rest of the flower we're going to throw away. Great. Now, they're not specifying any type of function to integrate. Therefore, we are just going to use number 1. And that would calculate the area of 1 petal. Now, if they build up this thing to some height, I don't know, cut it flat, So z equals 3, then you plug 3 in. You have two different functions, you subtract top minus bottom. So there's a lot of modifications to this same problem. So I have my double integral. I will use 1 over here because f of r theta is not given to me. R dr d theta. Don't forget this r. Keep telling yourself r dr d theta. Right? If you say it 15 times, you will eventually start sounding like a pirate, and you will not forget it. You will have fun too. You will go r dr d theta, and then it's right. It's fun. Okay. What is the, well, now the easy part is the function part, because it clearly goes from 0 to 2 sine 2 theta, right? That's that. The scary part now is the outer part, because we get to use only one petal of the flower, right? One petal. Now you might say, well, yeah, sure, one petal, what's the big deal? If it's a one petal thing and the whole thing is 2 pi, then clearly 0 to pi over 2, hold on, not clearly, all right? Because the flower in polar region is not drawn the same way like you artists will do, okay? When you draw the flower, eyes over there, when you draw the flower, the way I drew the flower was I put the petal here, then I move to the next one, then but that's just because I'm lame, okay? This thing is not done this way, right? It might do something like this. Right? Now, if that's the way it's drawn, sure, 0 to pi over 2. See? 0 to pi over 2, pi over 2 to pi, pi to 3 pi over 2, 3 pi over 2 to 2 pi, and it stops. Sure. You know how I'm going to know that? Well, I can actually start drawing this flower by hand in a chart, like in the middle school. You pick T's, right? And then you follow the T's. Or you can graph that in your TI-83 calculator, and then as soon as you push graph button, start staring at it, right? These calculators are designed in the past millennia. They're slow. And you can actually see the progression of the line. If you look at the back of the calculator, it says 1999, right? Design definitely predates you, okay? And they will say later years for 84s, but it's the same thing. 84s are just more memory and faster processor. But they're all going to be sluggish enough for you to see where it starts and when it follows. Now, if it draws the first petal completely, yeah, 0 to pi over 2, and we're done. Cool. But if it starts over here, and then jumps over there, and jumps over there, and jumps, and this is the last thing, then it's 3 pi over 2 to 2 pi. So you have to be very careful when it's drawn. Could be any one. Cosines are even crazier, because the cosine ones, they start here, and it goes like this. Oops. So the cosine one will start there, and then go here, and then go here, and then go here, and then go here, and then finish that. A cosine one, this one, is negative pi over 2 to pi over 2 for the first petal. So, yeah. You have to be careful. So let's graph this real quick in our calculators. Now you have to do a few things to your calculator before you can graph polar stuff. First step is to go into mode. You make sure that you are in radian, and then on the fourth line it says funds par pol c, secu, whatever it is. You have to go to POL, that says polar. So radian and polar, and then hit enter when it's polar. So, and then you go second quit, and then you're done with you. Then you go y equals, and now you will notice when you push y equals, it's no longer F1, F2, F3. It shows R1, R2, R3. So it's looking for R equals. If it still says F, whatever you put in is going to be garbage. So now 2 sine 2, and when you push the x variable, it will print theta. If you ever noticed, the x variable actually prints x, t, theta, and n. And that corresponds to those 4, funds, par, pol, and seq, right? Because those are the variables. The first one is function in terms of x, second one is parametric in terms of t, third one is polar in terms of theta, and the last one is sequences in terms of n. So you push this, and now when you hit graph, yep, it draws the first in the quadrant over there. So 0 to pi over 2. And now you go and compute this. The first order of business is to compute the inner integral. Inner integral is r squared over 2, so that's going to be 1/2 of 2 sine 2 theta, everything squared, d theta, 0 to pi over 2, 1/2 of the, so it's a 2 sine squared 2 theta, d theta. When you square 2, you get 4, and then half of 4 is still 2. And this is the time where you realize that you have to integrate sine squared. How do we integrate sine squared? How do we integrate sine squared? Power reducing formula. There's nothing else that works. Well, Mathematica, right? So, power reducing formula. This is equal to, hold on. This is equal to 0 to pi over 2, 2 times, and power reducing, can anyone help me? Very good. Nice, nice. You all have 4 theta over there because it doubles the angle. These 2's die. And now the integral of 1 is just theta, minus, and the integral of cosine is positive sine, so sine 4 theta over 4 because of the u sub. Everything computed 0 to pi over 2. Well, the functions are theta and sine, so we don't have to worry about 0. So we have a pi over 2 minus, and we plug in pi over 2, so that's sine of 2 pi, everything over 4, but that's 0, so the whole thing is pi over 2. We just did a 30-minute example, and just everyone is like, yeah, whatever, just keep moving. To be excited about this stuff. It's Calc3. You can use this to annoy others. What do you know? Can you compute this? They might know what the symbol means, the integral one, but I don't think they will be able to spell it, so there you go. And you can compute. So let's recap real quick. Yeah, I know we talk a lot for such a short example. Next slide. So we have domain, which is no longer a circle, or those concentric circles to create what we call annulus, which is the pipe base for the pipe. Now we have general regions, and general regions could be cardioid, could be whatever other shape you can come up with. You know that from Calc 2, so chapter 10. So when you open the chapter 10 polar graphs, guys, those graphs from chapter 10 are your domains now, and they end up in your limits, as you can see. And then the outer one, which is the theta. If you have something over here, you are computing volume. If you have 1, you're just computing area of the base. So this integral is actually equivalent to the one that you did for the area of these surfaces in your Calc 2 chapter 10 problems, except that the inner one was not expressed as the limits of another integral. It was expressed as you had the r squared over there and those kind of things. So yeah, all of this is cute, right? But why do we really need this in the era of computer when all of these integrals are solved by software? There is one instance where computers are still not developed enough to follow our brains. And that is the integral that can be converted into a polar integral. So you get to recognize the structure, right? And you get to convert from rectangular integral into a polar integral and then integrate like this, where the previous one was not possible. So computers are not too good in that situation. Of course they will be, but there is a little sanctuary for now, right? Where we are still relevant to some extent. So there we go. So let's see a problem where we as a species are still relevant. Anything from 23 through 28, 26. One day it's gonna cave in through the ceiling. Do what? Belts, he said. Yeah. We are asked to compute the integral of region R and then the region R is given as, and they gave us a polar region, which kind of gives it away. There we go. So now what? Well, everything is already in polar in terms of our limits. All I need to do is to make sure that this is in polar as well, and we're done. So I have r dr d theta, that's my dA in polar, divided by what? 1 plus r squared. Very good. 1 plus r squared. And then we have our limits, which are clearly stated, 0 to pi and 1 to 2. So please don't make this difficult, right? They gave you the straightforward limits. So let's rewrite this thing. So, how do we integrate this? And if you say inverse tangent, I will murder you in front of the whole online community over here. So how do we integrate this? U sub, thank you. This is a basic Calc 1 U sub thing. So, yeah, get busy.
Oh, really? Yeah.
What's the answer? What's the answer? How much?
0.346 pi.
Well, you can multiply by pi since you already have the decimal in front, right?
Oh, 1.08879.
Thank you. So you sub on the inner integral, and then the rest is walk in the park. Now this problem was too obvious. Problem 28 says e raised to the negative x squared minus y squared dA. And the region R is given in rectangular coordinates xy such that x squared plus y squared less equal than 9. See that? Everything that we have in this problem is in rectangular coordinates. What is the thing that gives it away that we are supposed to switch it to polar? X squared plus y squared. Yeah. But also, if you remember your Calc 2 from the beginning, right, actually chapter 7, integration by parts and so on, you know that you can integrate e to the x. You know that you can integrate x e to the x squared dx. And you know that, first x. And you know that you can integrate x e to the x squared dx. So this is Calc 1, this is Calc 2. The one that you cannot integrate is just pure e to the x squared dx. This one you cannot integrate unless you use power series, which I believe I had on my exam. Those of you who took my exam in Calc 2, third exam, had this problem. Integrate this. So you were supposed to change it, right? First 4 terms of the exponential Taylor expansion, and then you replace each x with x squared, and you're just integrating polynomials. So it's easy and quick from there. Now you have that type of a structure to integrate here. And this is going to become e to the negative r squared. Right? Did we win? Going from negative x squared to negative r squared. How does that make it better? How does it make it better?
There's going to be an R there, so you can...
There's gonna be an R there, R, the theta, and that R is a U sub for the exponent, right? So it turns into this, which is Calc 1, right? Yes, there's gonna be an R. When you develop this dA into R, the theta, there is an R to give you U sub. I'm just going to set this up, and then we're going to go with the next section. This is it. Hope you're not disappointed. So this thing is equal to double integral e to the negative r squared r d theta. And now we have our domain. Domain is the full circle. This is 3. So our r goes from 0 to 3 on the inner and 0 to 2 pi on the outer. It's kind of sneaky of them to put less than equal to 9. Because what is less than equal to 9 means is you get to shade that circle. And the circle starts at the center, right? For r, 0 to 3. Right? And when you go 0 to 3, then you are out on the x-axis, and then that 3, 0 swings 0 to 2 pi, right? So 0 to 3, and now 0 to 2 pi. And that will fill everything in, right? And that's this symbol here. It's one way to tell you that all of this over here is the domain. Step. Yes?
I just wanted to give you a heads up. I just realized I made a stupid error on the last one, and it's 1.439.
1.439. 1.439. All right, thank you. All good. We'll talk about it later. U equals negative r squared dr. No, this and du equals negative 2r dr equals to here. Just do it, right? And that's that. Let's do the next section.